All right, so here's the solution to the Vlooyberg Tower case study problem. So like we talked about in the last video, the problem basically reduces down to an 135 kilonewton force pointing downwards, applied 8.6 meters to the right of support A and 4.7 meters above support A and B. And what we want to find is the equivalent force couple system caused by this force at A, and then we want to take that equivalent force couple system and find the forces at A and B. So basically, we're just coming up with two different ways to show the loading on this tower. So the first thing that we have to understand to solve this problem, and the main concept of this problem, is that on any rigid body, if we have a force, we can move that force anywhere on the rigid body as long as we move the force and also apply at that point that we're moving the force the moment that that force causes about that new point. So that's kind of confusing to say in words, but it's kind of intuitive because it's just saying that if we were to move this force to A, we can just take this force and move it down to A, but then we also have to apply at A the moment that this force in its original location causes about A. So we're taking this force alone, moving it, and then replacing it with a force and a moment. And that moment, again, is the moment that this force causes about A. So I know I just said that like 3 times, but that's the most important part of the problem. And hopefully you can understand that in words, and if not, the textbook does a really good job of explaining it. So we go over here and we see that our answer is going to look something like this. So I've cut the rest of the tower, and here we just see the base. So we have supports A and B, and we want to find the force and the moment that is caused by that 135 kilonewton force. So the force is easy. We know that the force at A downward is just going to be 135 kilonewtons because when we move a force, that force itself retains the same magnitude and direction. But what we have to add now is this moment. So if we look back over here, we see that this force is a completely downward force, so it has no horizontal component, and we know the perpendicular distance. So by the definition of a moment, all we have to do to find the moment at A is multiply 135 kilonewtons, the force, by the perpendicular distance of 8.6 meters. So we go over here and do that, and the answer is 1,161 kilonewton meters clockwise. So our equivalent force couple system at A is going to look like this. So again, this loading here and that loading here are identical. They're the same thing. It's an equivalent force couple system. So we've replaced this loading entirely with this loading, and it gives the same exact effect. And that's the beauty of these types of problems, because we can take a system that has a lot of different forces all over the place and summarize it with one force and couple. And that's just simpler for us to deal with. Okay, so now that we know this, the second part of the problem asks us to take this and basically get rid of the couple, get rid of the moment. So now we have 2 forces, one at A and one at B. So we're finding the forces that this structure causes on A and B. We don't want the moment anymore. We don't want the couple. So the way we do that is we go back to the definition of a couple. We know that all a couple is 2 forces a certain distance apart with opposite magnitude. So in this case, we want the forces to be, we want to take this and turn it into 2 forces, one at A and one at B. And because of the sense of the moment, how the moment is turning clockwise, we know that the force at B is going to be facing downwards and the force at A is going to be facing upwards. So once we take this couple and turn it into 2 forces, we can then sum this original force and that new force, and then we'll have our force at B and we'll have our force at A, and that will be our answer. So we go down here and we look, the definition of a couple states that a couple is just a force times a distance, like a moment, except we have 2 forces in opposite direction. So we can find this FC by dividing our couple at A by the distance between A and B. And we were given that the distance between A and B was 1.5 meters. So we have 1,161 kilonewton meters divided by 1.5 meters, and that's 774 kilonewtons. And again, because of the sense of the moment, we know that this FC value, it's going to have a force here facing downwards and a force here facing upwards. And then the final step is just to sum this FC and the 135 kilonewtons applied at A. At B, we don't have to do any force summation because FC is the only force applied at B. But for A, we have to make sure that we combine these two forces because they're facing in opposite directions. So we do that. We do 774 kilonewtons minus 135 kilonewtons, and then we get our force at A to be 639 kilonewtons facing up, and our force at B, 774 kilonewtons facing down. So what we've done is we've taken this loading and we've completely replaced it with a force couple system, and then we've completely replaced it by a system of two forces. And we got that from, again, the definition of a couple. So hopefully this helped looking at the solution. Again, this isn't really a numerically challenging problem. It was more of a problem to really show the basic concepts of force couple systems, how to get from a loading like this to a simple force couple system, and then what can we do with that force couple system. In this case, we found the loading on each support. So again, if you have any questions, please leave them in the comments or send me an email or ask them. I'd love to help you out.